So this lesson is about significant figures, rounding, and calculations. And when we're dealing with significant figures, we are keeping our eye on the fact that mathematics can never make measurements more accurate than they are. So we start by looking at significant figures and what they are. Really, significant figures include these 4 points. Anything that's non-zero, so any non-zero digit. So in an example, say as 1.234, all 4 of those digits would be significant. Any zero that's embedded between 2 other numbers, such as 3.506, that as well would be 4 significant figures because the zero is embedded between 2 non-zero integers. Any trailing zero after a decimal. This usually specifies how accurate a measurement is. So those 3 zeros that come after the 4, they would be significant. The first zero is not a trailing zero, so it is not significant. But the trailing zeros are. And then any trailing zeros without a decimal place if we know that they're measured. So if I said 500 liters exactly, and we know that this is not 501 liters, it's not 499, this is 500 liters exactly, those 2 zeros would be considered significant. But only when we specify that it's exact. And in most of the calculations that we're going to do, we could consider those 2 zeros to be exactly measured. So here's an example. Let's determine the number of significant figures in each of the following. 527.3 kilograms. That would have 4 significant figures because all of them are non-zero and there are no embedded zeros, so that would be 4 significant figures. 5,050 meters per second. The zero that is embedded between the 2 5s is significant, and the trailing zero would be only significant if we were to assume that it was measured exactly. So this could be thought of as 3 significant figures if it wasn't specified, but 4 significant figures if we said that this was 5,050 meters per second squared exactly. 403 meters would be 3 significant figures, and 0.0045 would be 2 significant figures because the zeros that precede the 4 are not significant. This number could be expressed in scientific notation without losing any information. Measured quantities, such as, say, 1.7 meters and 1.700 meters, reflect the precision of an instrument. So the second value here, 1.700, was measured by a much more precise instrument and hence generated many significant figures. The number of digits always represents the accuracy of a measurement. And when we're doing calculations that involve measurements, the mathematics that you use to make the calculation can never make the answer more accurate than what we started with. And a good example of this is, say, if we're trying to find the circumference of a circle, and we measure the radius to, say, 2 significant figures. When we multiply by pi, the answer for circumference would be an infinitely accurate measurement. And of course, that can't happen. We can't allow mathematics to make our final answer more accurate than what we started with. And so that's why we pay attention to significant figures. So let's take a look at some calculations. In general, when we multiply or divide, the number of significant digits in the answer has to be limited to the number of digits in the least accurate measurement. So in this example, find the area of a rectangular carpet with these dimensions, 3.42 by 0.96. The 3.42 has 3 significant figures, and the 0.96 has 2 significant figures. So at the very end of the problem, once we make the calculations, we'll have to restrict our final answer to 2 significant figures. So let's do this problem. Area is equal to length times width for a rectangle. And here we'd have the 2 measurements. When we multiply these out, our calculator will give us a value, 3.2832 meters squared. And of course, this is much more accurate than what we started with, and we need to truncate this answer. So of course, 3.2832 to 2 significant figures is 3.3 meters squared because we round up the 2 because of the 8 preceding it. When we're working with addition and subtraction, we have a slightly different rule. The number of decimal places in the result is the same as the number of decimal places in the measurement with the fewest decimals. So find the perimeter of a garden with dimensions 2.0056 meters by 4.03 meters. So in the one measurement we have 4 decimal places, in the other measurement we only have 2. We're going to have to restrict our answer to 2 decimal places. So perimeter is equal to 2 times the length plus 2 times the width. And when we substitute our values for length and width, we come up with an answer. And when we add this answer in our calculator, we get 12.0712 meters. Of course, we need to restrict this to 2 decimal places, and so we get 12.0 meters. It is important to note that whenever we use combinations of multiplication and division and addition and subtraction, which is usually the case, always follow the rules for multiplication and division. Rounding. This is a slightly different topic, and we've alluded to it in the following 2 examples. When we round, we look at the figure following the one that we want to be last, i.e. the one that you want to drop. So if the digit is less than 5, we know that we don't change anything. We just drop the other numbers. It doesn't round it up. It doesn't round it down. There's just no change to that last decimal place, and we drop the other numbers. If the digit is greater than 5, including any 5 with a whole bunch of stuff after it, any non-zero digit after it, we round up. And if the digit is 5, then we always round to the nearest even, which means that if the digit is 5 and there's nothing after it, or there's a 0 after it, we round so that the number is even. So if it's 2, we leave it the same. If it's 3, we would round up to 4. Let's take a look at a few examples of this. We want to round each of the following to 3 significant digits. So 2.1634 meters. We want to round this to 3 significant figures, and so this is where we're going to draw the distinction, because 2.16 is 3 significant figures. So we look at the 3. 3 is not a number that's greater than 5, and so this just becomes 2.16 meters. 4.0057. We have to ask ourselves, what are we going to do with that final 0? Well, the number preceding that is 5, and there is stuff after it. There's a digit 7 there, so that tells us that we round up. So this becomes 4.01 kilograms. With 3.845, again, it's the 4 that we're looking at, and in this scenario, there is nothing that comes after the 5. So here we round to the nearest even, and since 4 is already an even number, we just leave it as such, 3.84 centimeters. The final example is 4.235 milligrams, and in this case, the 3 is not an even number, and so we would round to the nearest even here as well. This becomes 4.24 milligrams.